Hello, thank you for watching this talk entitled Interactions Between Colloidal Particles Mediated by Non-Absorbing Polymers, Cashmere and Anti-Cashmere Effects. I'm David Wang in the Department of Chemical and Biological Engineering at Colorado State University, and this work was done by my former postdoc, Pengfei Zhang, who is now a professor at Donghua University in China. Here we ask a simple question. What is the effective interaction between two hard or non-absorbing surfaces immersed in a homopolymer solution? These flat surfaces represent colloidal particles with a size much larger than the ruled mean square chain end-to-end distance Re. For simplicity, they are identical, homogeneous, and parallel to each other, and the confined system is in equilibrium with a bulk polymer solution. To make the problem even simpler, let's first consider athermal chains, so that the energy does not play a role here. Of course, a crucial difference between polymers and small molecules is the chain conformational entropy, which means that chains do not want to go into the confined space. We therefore have the well-known depletion attraction between the two surfaces. In fact, this is exactly what one obtains under the so-called ground state dominance approximation, or GSDA, which is a mean field theory valid in the limit of infinitely long chains. But then several experiments reported repulsion between the two surfaces when their separation distance d is somewhat larger than Re. Since GSDA neglects the chain end effects, two research groups performed the lattice self-consistent field, or SCF, calculations for chains of finite length and indeed found very weak repulsion. The effective interaction between the two surfaces is actually a damped oscillation as a function of d with the decay length proportional to the polymer coil size due to the liquid-like layering of polymer coils near the surfaces. Semenov also presented an end correction to GSDA referred to as the GSDE theory, which gives a weak repulsion caused by the formation of two virtual opposite polymer brushes due to the enrichment of chain ends near the surfaces. On the other hand, all these theories neglect the system fluctuations. Orbakov and Semenov showed that such fluctuations can also induce a repulsion between the two surfaces. They called it the anti-Cashmere effect. The best way to validate their theory is, of course, via molecular simulations. But the only relevant simulation we could find was done by Lewis and coworkers, who calculated in their lattice Monte Carlo simulations the interaction-free energy delta F as a function of the surface separation d shown by these circles. We hardly see any repulsion in their simulation result. It is therefore unclear whether the repulsion even exists, and if so, where does it mainly come from, the chain end or the fluctuation effects? We'd also like to see how it is affected by the solvent quality. So this motivated our work. We consider a model system of lattice polymers confined between two identical, impenetrable, and homogeneous surfaces, placed at x equals 0 and d plus 1 respectively, with the lateral area denoted by A. The confined system is in equilibrium with the bulk solution at the polymer volume fraction denoted by phi b. Also, we take the lattice spacing and kBt as the unit of length and energy respectively. This is the canonical partition function of our model system, where small n and ns are the number of polymer chains and solvent molecules of vacancies, respectively, and capital N the number of segments on each chain, capital R Ks the spatial position of the S segment on the K's chain, and small rj the spatial position of J's solvent molecule. So these two factorials account for the indistinguishability of polymer chains and solvent molecules, respectively. The blue and green terms sum over all system configurations. HC is used to ensure the connectivity of all chains, and HE gives the non-bounded interaction energy of the system, with epsilon being the attractive energy between two nearest neighbor polymer segments, and M the total number of such pairs. And finally, this red term enforces the system incompressibility, where ρ hat and ρ hat S denote the number of polymer segments and solvent molecules, respectively, at the lattice site R, with ρ naught equal to 1 corresponding to the self and mutual volume walk. With the canonical partition function Z, we can write the grand canonical partition function Kc, where μp and μs are the chemical potential of polymer chains and solvent molecules, respectively. Kc can be rewritten like this. where C is an unimportant constant, V the system volume, and mu the exchange chemical potential between one polymer chain and n solvent molecules. And finally, the effective interaction between the two surfaces is described by the reduced intersurface potential W star, which is essentially the difference in the grand potential omega between the confined and the bulk solutions. For this model system, we perform both lattice self-consistent field calculations, which corresponds to rho naught to infinity, thus neglect the system fluctuations and correlations, and the lattice Monte Carlo simulations with the self and mutual void walk. Direct comparisons between them therefore unambiguously quantify the fluctuation correlation effects neglected by the theory. In particular, in Monte Carlo simulations, we use our recently proposed Z method to directly estimate the canonical partition function Z as a function of the number of chains n at a given D. This is achieved by the one Landau sampling in the n space, where the trial moves of chain insertion and deletion with configurational bias are used. To avoid the error saturation problem and to improve the efficiency of the one Landau sampling, we also combine it with the optimized ensemble sampling. Our simulation results are therefore much more accurate than those of Lois and coworkers obtained using the repulsive wall method. For details, please refer to our paper here. Hereafter, we set the chain length n equal to 80 on the simple cubic lattice with the coordination number z equal to 6, and define the Flory-Hawkins chi parameter like this. Let's first look at the rule mean square chain end-to-end distance in the box solution REB, as this will be taken as the length scale for our subsequent results. This semi-logarithmic plot shows that in the athermal solution, REB obtained from Monte Carlo simulations decreases with the increasing polymer volume fraction phi b in the box solution, which is due to the increased screening of the intrachain interaction, repulsive in this case, by the interchain interaction. This is well known, and similar results are found as chi is increased to 0.3 and 0.6, or say the solvent quality decreases. As chi is further increased to 0.9, however, we see that REB increases with increasing phi b. This is again due to the increased screening of the intrachain interaction, which is not attractive by the interchain interaction. This table shows that the second variable coefficient b decreases with increasing chi, and it becomes negative at chi equal to 0.9, consistent with the plot here. Our Monte Carlo simulations actually gave the theta point to be around chi equal to 0.78. Note that due to the finite chain length used here, all these chi values are still below that at the critical point given by the Monte Carlo simulations as shown later. Finally, the self-consistent field theory gives ideal chain conformations in the box solution, thus a REB value smaller than the Monte Carlo results, due to its beam field approximation. Next, for the confined polymer solution in an athermal solvent at phi b equal to 0.4, this semi-logarithmic plot shows self-consistent field result of the reduced intersurface potential W star as a function of the separation distance d between the two surfaces, normalized by Re. We see the depletion attraction at small d, where W star is negative. Then, a positive maximum W star m, thus a very weak repulsion located at dm. As d further increases, W star exhibits a quickly damped oscillation around 0. We can quantify the range of this positive W star by the location of its first and second roots dA and dr, obtained from linear interpolation of data on the lattice. As I mentioned before, this very weak repulsion is due to the finite chain length, or equivalently, the chain ends. Here shows the corresponding results obtained from Monte Carlo simulations, where Re is taken to be the simulation results in the bulk solution that I showed you before. We see that the fluctuation-induced repulsion is more than one order of magnitude larger, and occurs at a smaller d over Re than that caused by chain ends. Similar results are found at other combinations of chi and phi b. We also see that increasing phi b, or decreasing chi, leads to stronger repulsion occurring at a smaller surface separation in both self-consistent field and Monte Carlo results. These results are obtained on a simple cubic lattice, and similar results are also found on a square lattice. In particular, the anti-Kashmir effect is weaker but occurs over a broader range of d over Re in 3D than in 2D. Finally, at phi b equal to 0.2 and chi equal to 0.6, the self-consistent field result gives no repulsion, because this is close to the mean field critical point, given here for n equal to 80. So W star in this case is always negative and quickly decays towards 0 with increasing d. At the mean field critical point, however, the self-consistent field result exhibits a long-range attraction, decaying with d to the power of -3, as shown by the straight line on this log-log plot. This is the Kashmir effect due to thermal fluctuations, first proposed by Fisher and de Gennes. According to their equation number 4, W star scales with d to this power at the critical point, where alpha and nu are the critical exponents. The mean field theory gives alpha equal to 0 and nu equal to 1/2, thus the -3 power law. On the other hand, if we use the hyperscaling relation 2 minus alpha equal to nu times d, with d being the dimensionality, we should find the -2 power law in Monte Carlo simulations at the critical point. But our simulations are not performed right at the critical point. Here show our Monte Carlo results at a chi value slightly below the critical value and at 3 bulk polymer concentrations around the critical concentration. We again see a long-range attraction shown in red close to the critical point, which decays approximately with d to the power of -1. As we move away from the critical concentration, the decay becomes much faster. While this power law is not what we'd expect right at the critical point, the Kashmir effect leads to strong depletion of polymers from the confined solution, even when d is about 10 times Re, as shown by this semi-logarithmic plot of the ratio between the average polymer volume fraction in the confined solution phi bar to phi b as a function of d. We see that the blue curves showing the Kashmir effect obtained near the critical point of the bulk solution are in great contrast to other cases away from the critical point. So to summarize, we have performed both self-consistent field calculations and Monte Carlo simulations based on the same model system to examine the effective interaction between two identical, impenetrable, homogeneous, flat, and parallel surfaces, mediated by homopolymers confined between them and in equilibrium with the bulk solution. Direct comparisons between the self-consistent field and Monte Carlo results, without any parameter fitting, therefore unambiguously quantify the effects of system fluctuations correlations neglected by the self-consistent field theory. We have found fluctuation-induced repulsion, or the anti-Kashmir effect, between the two surfaces at d over Re equal to 0.7 to 2, which is about 1 order of magnitude stronger than the repulsion due solely to the finite chain length given by the self-consistent field theory. It becomes stronger and occurs at a smaller d over Re with increasing bulk polymer volume fraction or solvent quality, and is weaker but occurs over a broader range of d over Re in 3D than in 2D. Finally, near the critical point of the bulk solution, we have also found the long-range attraction, or the Kashmir effect, between the two surfaces, which leads to strong depletion of polymers even at d over Re equal to 10. Details are given in these two papers. Thank you for your attention, and I'd be happy to answer any questions you may have.